So today or tonight, we are going to talk about problem solving and creativity. The following chapter, I must say that I it's a bit complicated to study, and I admit that I myself considered it as a problem to solve, and I attempted to solve it in an insightful manner naman. And let's proceed. So here are some of the questions we will explore in this chapter. First, what are some key steps involved in solving problems? What are the differences between problems that have a clear path to a solution versus problems that do not? What are some of the obstacles and aids to problem solving, and how does expertise affect problem solving? And lastly, what is creativity and how can it be fostered? In short, the chapter comprises the processes of problem solving and effort to overcome obstacles that hinders the path to a solution, and also the role of creativity in problem solving. Now, eyes on the picture. Try to analyze the picture as I read the problem. Imagine that you were the person standing in the middle of this room, in which two strings are hanging down from the ceiling. Your goal is to tie together the two strings, but neither string is long enough so that you can reach out and grab the other string while holding either of the two strings. You have available few clean paint brushes, a can of paint, and a heavy canvas tarpaulin. How will you tie together the two strings? We will just take a moment, pause this video, and try to analyze. And if you're having trouble finding a solution, we'll proceed to look at the figure 11.7 in the following slides. So in problem solving, we have steps or cycle to consider. First, problem identification. Do we actually have a problem? Second, definition of problem. What exactly is our problem? Then, strategy formulation. How can we solve the problem? This is all about formulating strategies and considering analysis. Means breaking down the whole of a complex problem into a manageable elements. And also to consider the process of synthesis, the putting together various elements to arrange them into something useful. So that's in the formulation of strategies. And fourth, organizing information about a problem or organization of informations. How do the various pieces of information in the problem fit together or match together? And fifth, allocation of resources. How much time, effort, money, etc. should I put into this problem? Remember the appropriate lang, or not the extravaganza. Just something that fits into this problem. 6. Monitoring problem solving. Am I on track as I proceed to solve the problem? Is it still in the allocated time? Am I still in the right path or settings, or basin it is beyond na? 7. Evaluating problem solving. Did I solve the problem correctly? Now, a personal example where I subconsciously apply the problem solving cycle. First, problem identification. I don't have a laptop. That is my problem. I have a problem that exists because I don't have a laptop to use. so that I can proceed to make this report. Definition of problem. So that is exactly my problem. I don't have a laptop. That is specified. But problem identification, I know that I have a problem, that it exists through the lack of laptop, lack of resources to use. Third, constructing a strategy. I have a strategy formulation in a way that I ask my uncle, my tío, for his laptop so that I can start this report. And also, I have another problem. The house is very rowdy at daytime rather. So I have to make it in the nighttime. So that is my strategy. I borrow the laptop in the night for organizing information about the problem. I don't know if I actually apply this to how do the various pieces of information in the problem fit together. Well, I think I did. Fifth, allocation of resources. How much time, effort, money should I put into this problem? So time, I allocated my time in my mind. I had it in mind. I planned it in my mind. I planned it on my mind when I should start doing this report. 6. I monitor the problem through always checking on my tío if the laptop is free to use, and I evaluate the problem. Did I solve the problem correctly? Perhaps I did, because I'm already working on the report. There are types of problems: the well-structured problems and the ill-structured problems. Well-structured problems have clear paths of solutions, while ill-structured problems lack of clear path solutions. Well-structured problems, in particular, there is an application of a formula. Kumbaga sa test, this is the objective na ay multiple choice whatsoever. While the ill-structured problems is the essay, where you have to be insightful. This is subjective. So let's further discuss well-structured problems. An example for well-structured problems in cognitive psychology, yes, in ecological researches, is the move problems, where it requires a series of moves to reach a final goal. The most well-known move problem involves two antagonistic parties. I have here an example. This is the 3 hobbits and 3 orcs at the river bank. So the problem: 3 hobbits and 3 orcs. 3 hobbits and 3 orcs are on a river bank. The hobbits and orcs need to cross over to the other side of the river. The other side of the river, which is this. They have, for this purpose, a small rowboat that will hold just 2 people. This is the rowboat. There is one problem. If the number of orcs on either river bank exceeds the number of hobbits in that bank, the orcs will eat the hobbits on that bank. How can 6 all creatures get across to the other side of the river in a way that guarantees that they all arrive there with the forest? So problem space and problem solving cycle is basically alike, but then problem space are simulated or imitated to your computers. So in well-structured problems, in the computers, algorithms are sequences of operations in a problem space that may be repeated over and over again and that in theory guarantee the solutions to a problem. So this is a process or set of rules to be followed in calculations or other problem-solving operations, especially by a computer. It generally continues until it satisfies a condition determined by a program. So, suppose a computer is provided with a well-defined problem and an appropriate hierarchy of operations and organized into procedural algorithms. And the computer can calculate all the possible operations and combinations of operations within the problem space. But unlike computers, the human mind does not specialize in high-speed computations and numerous possible combinations. So Newell and Simon recognize these limits and observe that humans must use mental shortcuts for solving problems. This is, in a way, informal, intuitive, speculative strategies that sometimes lead to an effective solution and sometimes do not. So, kumbaga, to solve the problems instantly, we just refer to our common sense or knowledge without even proper validation, and sometimes it is tumpak and sometimes it is not. So heuristics, yeah? Examples of heuristics are intuitive judgment, stereotyping, educated guess, rule of thumb, profiling, and common sense. Remember that heuristic techniques are ideal as a quick fix, but can introduce error, bias, and may constrain creativity. So, next we have these isomorphic problems. So this is an example of a well-structured problem. Two problems that differ in content but have the same formal structure, as you can see. So we have here, compare the problems illustrated in the games of A, number Scrabble, B, tic-tac-toe, and C, magic square. Number Scrabble is based on equations, which triples of numbers satisfy the equation x plus y plus z plus 15. Tic-tac-toe requires 1 to produce 3x or 3 O's in a row, column or diagonal. The magic square requires 1 to place numbers in the tic-tac-toe board so that every row, column, and major diagonal adds up to 15. In what ways are these problems isomorphic? How do their differences in presentations affect the ease of representing and solving these problems? Although these problems seem different on their surface, they all require the same mental operations for their solution. So to be honest, I've never encountered the number Scrabble, or maybe I have, but I forgot already. But here in tic-tac-toe, since I can say that we can apply heuristics here, we randomly select where we put X, O, whatsoever. And here in Magic Box, it's like Sudoku, where you use your mathematical skills. It requires each lined up number should be equals to 15. So these are isomorphic problems because the games are mathematically equivalent. They are likely to differ psychologically because they require different sorts of information. Numbers Scrabble here is a numerical game requiring addition and subtractions of numbers, where tic-tac-toe requires a spatial representation which can only be disposed of with some difficulty even by fairly experienced players. Diba? And on the other hand, It is very easy, though maybe not likely to happen, to have one's moves in number Scrabble determined by superimposing it on the tic-tac-toe configuration, thus using the spatial magic square. So they are in a way isomorphic. They have the same formal structure, but they do not require the same mechanics. So in this move problem, so people refer to a state that is further from the end goal. For instance, moving all the Earth's inhabitants back to the first side of the river. And second, making illegal moves. They make an illegal move, that is, a move that is not permitted according to the terms of the problem. For example, a move that resulted in having more than 2 individuals in the boat would be illegal. Having 2 more individuals, this is not possible. Third, not realizing the nature of the next legal move. They become stuck. They do not know what to do next given the current stage of the problem. An example would be realizing that you must bring one orc habit back across the river to its starting point before you can move any of the remaining characters. So today, well-structured problems. Researchers are now developing computer simulations to solve well-defined problems or well-structured problems by the problem solvers. The problem solvers can be a human or an artificial intelligence. In that, for example, the chess game or the solitaire installed in your computers. And there, they must view the initial problem state and the goal state within this problem space, which is a universe of all possible actions to be applied to solving a problem. So problem space. It should contain possible strategies from the initial problem to the solution. So these are the strategies from problem to the solution. So it basically refers to the entire range of components that exist in the process of finding a solution to a problem. This range starts with defining the problem and then proceeds to the intermediate stage of identifying and testing possible solutions. So it ends with the final stage of choosing and implementing a solution. So it basically it becomes smaller. It gets smaller and smaller when you choose and implement the solution. Thus, it includes all of the smaller steps that exist between these identified stages. So, example, you might be realizing that you don't have the right clothes for a social event. Then identify what you need and where to go to buy the appropriate clothes, and then buying those clothes and bringing them home. In between these stages, you also have to take into consideration other associated concerns like, what can I afford? What stores carry what I want to buy? And then how do I find the time to shop for what I'm looking for? Basically, it looks like the cycle of problem solving. So as I've mentioned earlier, ill-structured problems are pretty much subjective. It requires an insight. So as the string problem, let's solve the string problem. Many people assume that they must find a way to move themselves towards each strings, and then bring the two strings together. They fail to consider the possibility of finding a way to get one of the strings to move toward them, such as by trying something to one of the strings, like these paintbrush. then swinging the object as a pendulum, and grabbing the object when it swings close to the other string. There is nothing in the problem that suggests that the person must move, rather than that the string may move. Nevertheless, most people suppose that the constraint exists by placing an unnecessary and unwarranted constraint on themselves. People make them insoluble. So, it is a matter of insights. Thus, it brings us to the ill-structured problems and the role of insight. Another example, a woman who lives in a small town married 20 different men in the same town. All of them are still living and she never divorced any of them, yet she broke no laws. How could she do this? You can formulate any ideas on why the woman broke no laws. How could she do all of that? It's a matter of insight, guys. So you see, ill-structured problems are insight problems because you need to see the problem in a novel way. Ill-structured. So now, let's see the solution to our problem here. The woman who married 20 different men and broke no laws at all. So the woman was involved in multiple. It could be that the woman who was involved in multiple marriages is a minister. The critical element for solving this problem is to recognize that the word married may be used to describe the performance of the marriage ceremony. So the minister married the 20 men but did not herself become wedded to any of them. To solve this problem, you had to redefine your interpretation of the term married. Others have suggested yet additional possibilities. For example, perhaps the woman was an actress and only married the men in her role as an actress. Or perhaps the woman's multiple marriages were annulled, so she never technically divorced any of the men, and I prefer the latter. I'd like to agree to the latter reason. So proceeding to the early Gestaltist views on insight. Gestalt psychologist Max Wertheimer, 1945 or 1959, wrote about productive thinking or the insightful thinking. He distinguished it from reproductive thinking, which is based on existing associations involving what is already known, but it is fundamentally different in a way that in solving insight problems given in the structure, you had to break away from your existing associations and see each problem in an entirely new light. But productive thinking can also be applied or used to well-structured problems. And we have here Wolfgang Kohler, a colleague of Wertheimer's. He studied insight in non-human primates, particularly a caged chimpanzee named Sultan. According to Kohler, the ape's behavior illustrated insight. As you can see, Kohler placed an ape in an enclosure with a few boxes. At the top of the cage, just out of reach, was a bunch of bananas. After the ape successfully tried to jump and to stretch to reach the bananas, the ape showed sudden insight. The ape realized that the boxes could be stacked on top of one another to make a structure tall enough to reach the bunch of bananas. So, to Kohler and other Gestaltes, insight is a special process. It involves thinking that differs from normal linear information processing. Moving forward to the obstacles and aids to problem solving. Here are some factors that perhaps hinder or perhaps an aid for problem solving. Mental set. A factor that hinders problem solving, a frame of mind where you are already fixated to a possible solution or procedure that you think normally works in many problems, but actually not in that particular problem. So for example, imagine that you are trying to solve a math problem in your algebra class. The problem seems similar to ones you have worked on previously, so you approach solving it in the same way. Because of your mental set, you are unable to see a simpler solution that might be possible. I think this happens to me all the time. And I think to yours as well. Don't know. So these mental sets can sometimes lead to rigid thinking and can create difficulties in the problem-solving process. So it is important to have knowledge in problem solving rather. So expertise is also required in problem solving. It is pure skills or achievement reflecting a well-developed and well-organized knowledge base. It can be good enhancement for problem solving. Moving forward to a type of mental set, we have functional fixedness or fixedness. It involves a tendency to see objects as only working in a particular way. It prevents us from solving new problems by using old tools in a novel way. It's just a specific type of mental self that involves only being able to see solutions that involve using objects in their normal or expected manner. Like for example, water. This is just a simple and I don't know, a dumb example, but water. You only see water as a cure for your thirst. But actually, there is another use for water. To water plants. Plants also need water. And another type of mental set is stereotypes, an aspect of social cognition in a way where belief that members of a social group tend more or less uniformly to have particular types of characteristics. You tend to overgeneralize from your limited observations. You observe a particular instance of set of instances, then it became a pattern, and then you would just expect that to happen all the time. This will tend to assume that all of the future instances similarly will demonstrate a pattern. Like for example, you observe that some African Americans can run very fast. If you then conclude that every African American is a fast runner, you have a stereotype because not every African American is a fast runner. Of course, when the stereotypes are used to target particularly scapegoats for societal mistreatment, grave social consequences result for the targets of stereotypes. And the targets are not only ones to suffer from stereotypes. However, like other kinds of mental sets, stereotypes hinder the problem-solving abilities of the individuals who use them. These people limit their thinking by using set stereotypes. What about negative and positive transfer? What is transfer, first of all? It is any carryover of knowledge or skills from one problem situation to another. And what the differences of positive transfer and negative transfer is that positive transfer occurs when the solution of an earlier problem makes it easier to solve a new problem, while negative occurs when solving an earlier problem makes it harder to solve a later one. So an example for a positive transfer would be one may transfer early math skills such as addition to advanced math problems, the kinds found in algebra or physics. While on the other hand, negative transfer, for example, may occur when police may have difficulty solving a political crime because such a crime differs so much from the kinds of crime that they typically deal with. Or when presented with a new tool, a person may operate it in a way similar to the way in which he or she operated a tool with which he or she was already familiar. So, moving forward to the incubation. This is taking a break when solving a problem. During this break, you must not consciously think about the problem. Allow the possibility that the problem will be processed subconsciously. Basically, incubation is putting the problem aside for a while without consciously thinking about it. Offers one way in which to minimize negative transfer. So it means taking a break from all the stages of problem solving. Neuroscience of problem solving. Frontal lobes and prefrontal cortex are essential for planning for complex problem solving. Both problem solving and planning ability decline traumatic brain injuries, and that is an advantage. The premotor cortex and the parietal regions activates if there is a need for attention and planning for movement. Now moving forward to the expertise, knowledge and problem solving. Now, so I've mentioned earlier that expertise is superior skills or achievement reflecting a well-developed and well-organized knowledge base. So knowledge. According to Wheaton and Gracer 2003, knowledge can interact with understanding problem solving as well. And even people who don't have expertise in cognitive psychology recognize that knowledge, particularly expert knowledge, greatly enhances solving problems. What interests cognitive psychologists is the reason that expertise enhances problem solving in a way that it answers the question, why can experts solve problems in their field more successfully than can novices? Do experts know more problem solving in algorithms, heuristics, and other strategies? Do experts know better strategies, and such questions? So, learners do better when they are presented a new material in coherent way. Such in the study of investigating how knowledge interacts with coherence of a text. The investigators presented children with biology text. Half of the children in the study had high levels of domain knowledge about biology and half had low levels. In addition, half the texts were highly coherent, meaning that they made clear how the various concepts in the text related to each other. The other half of the texts were low coherence, meaning that they were more difficult to read because the ideas did not flow smoothly. Readers then had to do a variety of problem-solving tasks because of what they had read. So, as the authors predicted, participants with low domain knowledge performed better when the texts were highly coherent. This finding suggests that, in general, learners do better when they represent new material in a coherent way. Surprisingly, however, the high knowledge group performed better than the texts were of low rather than the high coherence. So the authors of the study suggested that high knowledge readers may have been essentially on automatic pilot in reading the high coherence text, not paying much attention because they thought they knew what was in the text. The low coherence text forced them to pay attention. These results point out the importance of attentional processes when people solve problems. This is particularly relevant in domains in which they are expert and in which they therefore may not feel they have to pay attention. So here we have experts versus novices in terms of having a knowledge. Knowledge characteristics of an expert. Their large store of domain-specific knowledge richly interconnected and hierarchically structured, integrated multiple representations. On the other hand, novices' characteristics in knowledge, they have sparse knowledge set, disconnected and amorphous structure, poorly formed and unrelated representations. In experts, they have these problem-solving behavior. Conceptual knowledge impacts problem-solving, performs qualitative analysis, and uses forward-looking concept-based strategies. While novices, on the other hand, they problem-solving largely independent of concepts, manipulates equations, uses backward-look backward-looking means and techniques. So, in novices versus experts in terms of knowledge, statements made by problem solvers are called verbal protocols. For novice problem solvers, communicating problem-solving strategies improves performance. On the other hand, the experts appear to spend proportionally more time determining how to represent a problem than do novices, but they spend much less time than do novices actually implementing the strategy for solutions. So, as you can see, experts are very have these advantages on problem solving rather on novices. They are factual, they base on facts, while on the other hand, novices are only basing from their experiences. So once experts find the correct match, they quickly can retrieve and implement a problem strategy, while novices go from asking what they need to find out to asking what information is offered and what strategies do they know that can help them find the missing information. Often, novices use means-ends analysis. Thus, novices often consider more possible strategies than experts consider. For experts, though, means-ends analysis of problem serves only as a backup strategy. They turn to it only if they are unable to retrieve an appropriate strategy based on their existing schemas. So, experts are really ahead in terms of strategies. Now, artificial intelligence and expertise. Computers cannot actually think, they must be programmed to behave as though they are thinking. And they must be programmed to simulate cognitive processes. In this way, they give us insight to the details of how people process information cognitively. So, computers can be given highly complex instructions. Computer programs, more commonly known as software, programs tells the computer how to respond to new information. Now, the Turing test. So this is Alan Turing. In 1963, Alan Turing attempted to deal with the issue of whether a computer program can be intelligent. This is the first serious attempt. And the idea of the test is to find out whether an observer can distinguish the performance of a computer from that of a human. However, the criterion of whether computer performance matches that of humans is no longer relevant. Instead, the criterion of interest is that of how well the computer can perform the task assigned to it. Expert systems. These is also important in problem solving in computers. These are computer programs that can be performed the way an expert doesn't offer the specific domain. More likely base rules that are followed and worked down like a decision tree. So, several programs were developed to diagnose various kinds of medical disorders like cancer. Such programs are obviously of enormous potential significance given that very high costs of incorrect diagnosis. Not only are there expert systems for use by doctors, but there are even medical expert systems online for use by consumers who would like to do analysis of their symptoms. So this is the job of the expert systems in problem solving in AI. Moving forward to creativity. So most investigators in the field of creativity would broadly define creativity as the process of producing something that is both original and worthwhile. That something could take many forms. It might be a theory, a dance, a chemical, a process or procedure, a story, a symphony, or almost anything else. So what does it take to create something original and worthwhile? What are creative people like? So what are the characteristics of creative people? So highly creative individuals work long and hard. They study the work of their predecessors and their contemporaries. They thereby become thoroughly expert in their fields. They then build on diverge from what they know to create innovative approaches and products, and thereby change society. So, some computer programs such as those composing music or discovering scientific principles can be viewed as creative. Personality and motivation play important roles in creativity. To be a creative individual, a motivation can also be a factor. You have your intrinsic and extrinsic motivation. Intrinsic motivators might include sheer enjoyment of the creative process or personal desire to solve a problem, while extrinsic motivators might include a desire for fame or fortune. You can see the difference of them. It's like the intrinsic is more on being authentic, being the authentic self, while extrinsic is more into materialistic self. Creativity. It needs to be viewed in the context in which it occurs. So evolutionary thinking also can be used to study creativity. Neuroscience and creativity. The prefrontal regions are especially active during the creative process, regardless of whether the creative thought is effortful or spontaneous. A thinning of the left frontal lobe, lingual, cuneus, angular, inferior parietal, and fusiform gyri is connected with high scores on creativity measures. A relative thickness of the right posterior cingulate gyrus and right angular gyrus was related to higher creativity as well. These variations in cortical thickness, and especially a thinning in various areas, probably influence information flow within the brain. So that is for today. Thanks for watching.